Is my Gator one. So to start off with the question 2 about how I found the pK values. So I used, at least for the amino acids that are found on Earth, I used the pK value table as reference, and I also accounted for the fact that there's an extra methylene carbon in the J820 backbone. So this means that the if inductive effect of this carboxyl group is going to be a bit stronger because the inductive effect of the amine group is going to be less. And so this electron withdrawing effect is going to make the R group a bit more acidic, which means the pK values are going to lower a little. So arginine going from 12.5 to 12.3, at least that's how I've done it. Glutamate, I made it 4.1 from 4.3. Lysine, I lowered it to 10.2 from 10.5. Histidine from 6 to 5.8. And lastly, the C terminus from 1.8 to 1.7. Next up, about the novel amino acids. Well, I used the most similar amino acids, the ones that they were most closely similar to. So to start off, we have O. We have this amine thing that's most closely similar to lysine, which is actually right next to it. Except lysine has 4 methylene carbons and this has none, so it's actually going to be quite a bit more acidic. So that's why instead of a 10.5 from lysine, I've made this pK around 9.3. Next up we have X. X is basically methionine except it has one less methylene carbon, but methionine is not polar, so this is not going to be polar anyways either. So next up we have U. U is this carboxylic acid derivative that's most similar to aspartic acid. Aspartic acid has one methylene carbon while this has none. So for that reason it's going to be slightly more acidic. So that's why I've made its pK 2.7. Lastly, we have this. This is J, which is most closely associated with serine. Serine has one methylene carbon, whereas this has two. So this is going to be the opposite. It's actually going to be slightly more basic. So serine has a pK of around 13, and also I made J around 13.1. Next up on question 2, I used thrombinin for my protein. So I've used JMOL to visualize it. So to start off, I'm going to be looking at the buried alpha helix. So my alpha helices are colored purple and red. The purple is the buried part. So these residues are going to be non-polar residues that are facing the inside of the protein. They're facing the inside of the protein because they don't want to react with, or they don't want to be in phase with the polar outside because these are non-polar residues and they don't react well with polar solvents. And so for these, as we can see in the bottom left, these residues are like valine and tryptophan and leucine. These are nonpolar residues that are going to be interacting with hydrophobic interactions on the inside. Next up, we'll be looking at the solvent-exposed residues, alpha helix. And so these residues are going to be polar. They're going to be facing the outside, which means they're going to be facing polar solvents and going to be reacting with it well. So these residues are going to be like aspartic acid, lysine, tryptophan, sorry, not tryptophan. Hello. A lysine, another lysine. So these are going to be polar residues that are going to be interacting well with the outside. Next up, I'm going to be looking at some hydrogen bonding, some intramolecular hydrogen bonding. And so these are going to be shown by the dashed lines. So in this right here, this is going to be within the same polypeptide chain because it's within the same pink chain. So this is intramolecular. So for these residues, we have lysine and we have glutamate. So glutamate has this negative oxygen that's going to be hydrogen bond acceptor, and lysine has a nitrogen, which is going to be hydrogen bond donor. And so these residues are going to come together through hydrogen bonding, which is why we see this folding here, this non-covalent linkage that's inducing this folding. Next up, I'll be looking at intramolecular disulfide linkages, and my disulfide linkages are going to be shown by this green cylinder. So disulfide bonds are going to be formed between cysteine residues because these dioesters come together are in oxidizing conditions and form these covalent linkages. So these are going to be cysteine residues, as we can see in the bottom. Cysteine is the only one, at least in human bodies, that forms these disulfide linkages. Next up, I'll be looking at an intermolecular. So this is between an intermolecular disulfide linkage. So this is between this blue polypeptide chain and the red polypeptide chain. So it's two polypeptide chains coming together through a covalent linkage in the form of a disulfide bond. And so again, this is going to be cysteine and cysteine because cysteine is the only one that can do this with its dioester. Lastly, a fun fact about myself is that I am a pre-med. That's not that fun. A lot of people do it, but I am a Spanish minor. I've actually been studying Spanish for 8 years, and I actually studied abroad last semester in Peru.